Okay, here's a quick tutorial on section 4.6 permutations. So far in this chapter, we've looked at lots of different probability problems. We started off with experimental probability, then did some theoretical probability, then conditional probability, probability using sets. What we're going to get into for the next two lessons are different types of counting problems. So being able to count different types, being able to count the number of outcomes for different types of problems. So the first counting method we're going to look at is called permutations. So what a permutation is, a permutation means an ordered arrangement of objects. So the key word when you think permutations, think about the order of objects. So when we talk about how many permutations are there for a set of objects, that means how many different ways could we arrange those objects in different orders. So let's start off with an investigation here. So you're trying to put three children represented by the letters A, B, and C. So we have child A, child B, child C. We want to put them in line for a game. How many different orders are there? How many different orders are possible for the letters A, B, and C? So if you want to think about it, we could have A, then B, then C. So child A, then child B, then C. Or maybe A, then C, then B. Or maybe B, then C, then A. There's lots of different orders. I don't want to have to write them all out. If you wanted to write them all out, one method could be a tree diagram. We'll do that to start with, but I don't want to have to write them all every time. So I'm going to show you how to mathematically figure it out in a minute. But first, let's start off by using a tree diagram, just so maybe it'll help us understand the algebraic method we get to in a minute. So let's start off with the tree diagram. So that means, okay, so let's think. We want to put A, B, and C in order. We need to think, okay, so I could start off with child A, or I could start with child B, or I could start with child C. And from there, okay, if I started with child A, who could be next? It could be child B or child C. If I started with child B, the next one could be A or C. If I started with child C, the next one could be A or B. Okay, now the last branch of our tree diagram. If I started with A and then went to child B, the last option would be child C. If I started with A and then chose C, my last option would be B. If I went BA, the last one would be C. If I went BC, the last one would be A. If I went CA, I'd have to go B for my third kid. And for CB, I'd have to go A for my third kid. So there are 1, 2, 3, 4, 5, 6 different arrangements of kids. I could go A, B, C. There's one possible arrangement. I could go A, C, B, and so on. There's 6 different arrangements. Another way we could have figured out how many different arrangements are there, we could have used the multiplication rule for counting. We looked at that in earlier lessons in this chapter. Basically what it says, find the product of possible outcomes at each step in the sequence. If you want to know how many outcomes are possible, find out how many outcomes are possible at each step, how many outcomes are possible at each step, and multiply them together. That's what it means by find the product of possible outcomes at each step. So if we think about it that way, remember we have kid A, kid B, kid C. So if I'm putting the kids in a line, how many options do I have for the first kid? Well, I could take, I want to write these separately. So I have kid A, kid B, kid C. I could take kid A, and I could choose him to be first. Or I could take kid B, choose him to be first. Or I could take kid C. So I have 3 options. I have 3 options for the first kid. So I have 3 options. Now let's say I chose kid A to be first. So he's now gone. How many options do I have for the second kid? Well, I could put B or C for the second kid. So I have 2 options for the second kid. So let's say I chose B. How many options do I have left for the third kid? Given that I've now chosen someone to be the first and the second in line, I now have 1 option left. All I can do is take C and put it there. So I have 1 option for the third kid. And that relates exactly to our tree diagram. The first level of our tree diagram, we had 3 options, 3 branches for the first level. For the second level of the tree diagram, after I picked one person, I now have 2 options for the second level. And for the third level, there was only 1 option. That's where this 3 times 2 times 1 comes from. So the multiplication rule from counting says find the product of the possible outcomes, 3, 2, and 1, at each step in the sequence, and that'll tell you the total number of possible outcomes. So 3 times 2 times 1 is equal to 6 ordered arrangements of the kids. All right, here's a nice definition of permutations for you here. Okay, so the ordering problem in the investigation dealt with arranging 3 children to create sequences with different orders. So when you think orders, you want to think permutations. Okay, I keep stressing that because the next lesson is going to be on combinations, where the order of the objects is not important. But permutations, the order is very important for the objects. So if we consider n items, sometimes we want to know the number of different ordered arrangements. That means permutations. We want to figure out the number of permutations of the n items that are possible. So a permutation is an ordered arrangement of objects. The number of different permutations of n objects is equal to n factorial. And hopefully you remember what a factorial is. If you look back here, 3 times 2 times 1, anytime you have factors that are reducing by 1 each time being multiplied together, if they reduce all the way down to 1 by increments of 1, then you have what's called a factorial. 3 times 2 times 1 could be written as 3 factorial. 3 factorial means 3 times 2 times 1. Let's say we had 5 factorial. What would that mean? That would mean 5 times 4 times 3 times 2 times 1. The factors reduce by 1 each time and it goes down to 1. Okay, so if we want to calculate the number of different permutations or ordered arrangements of n objects, all you have to do is n factorial. And why do we have to do that? Well, let's say we have 5 objects. I want to put them in order. How many different options do I have for the first object? There would be 5 options for the first object. So there's 5 spots. I would then have 4 options for the second spot because I've used 1 for the first spot, 3 options for the next spot, then 2 options for the next spot, then 1 option for the last spot. To figure out the total number of possible outcomes, multiply the total number of possibilities at each step in the sequence together, and this what we have here is equivalent to 5 factorial. That's why you can just do n factorial to figure out the number of ranges of n distinct objects. So let's do an example for this. Okay, well, let me just show you this here just to help make sure you're okay with solving factorials. Factorial notation, so it's an exclamation mark, that means factorial. It represents the number of ordered arrangements of n objects. So for example, if we have n factorial, to expand that out, you reduce n by 1 each time. So after n would be 1 less than n, then 2 less than n, all the way down to 1. So 3 factorial, we went through that, it means 3 times 2 times 1, which equals 6. Also here, it's going to be important to be able to simplify factorials that are written as a fraction. So we have 75 factorial over 72 factorial. So what's 75 factorial? That means 75 times 74 times 73 times 72 all the way down to times 1. So I'm going to skip a bunch all the way down to times 1. What's 72 factorial? 72 factorial is 72 times 71 times 70 times all the way down to times 1. Now you should notice we can cancel out a significant number of factors on the top and the bottom. At the top here, I have 72 times all the way down to times 1. So 72 times 71 times 70 all the way down to 1. That will cancel out with what we have on the bottom. We have the same thing, 72 times 71 times 70 all the way down to times 1. So what we have here, what we have left is just 75 times 74 times 73. I'm not going to go ahead and evaluate that. You could evaluate that, type that in your calculator, and you get the answer, okay? Let's go ahead and do an example. So a horse race has 8 entries. Assuming that there are no ties, and how many different orders, so when you see order, you want to think permutations, can the horses finish in? So how many different orders can the horses finish? So we have 8 horses, so keep in mind, this is the number of objects we have, that's our n. If we want to figure out the number of arrangements of n objects, all you have to do is n factorial. So all you have to do is 8 factorial. And what's 8 factorial? That's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, you probably don't want to type all of that in on your calculator, so I'll show you the shortcut. If you want to type a factorial on your TI-83, just type 8, math, go over to probability, and it's number 4 is the factorial button. 8 factorial is equal to 40,320. 40,320. So there are 40,320 ways that the 8 horses can finish in. Okay? So those are a different number of ordered arrangements of the 8 horses. Why does 8 factorial work? Let me try and show you one more time again. So if we want to figure out the number of possible outcomes in a sequence of events, you have to figure out the product of the number of outcomes in each sequence. So if we want to think about it, in the horse race, one horse is going to finish first, second, third, fourth, fifth, sixth, seventh, and eighth. Well, how many possible horses could finish first? Well, there's 8 horses. Any one of the 8 could finish first. So one of those 8 is going to finish first. That means there are 7 horses left to finish second. And there are 6 horses left to finish third, and then 5 to finish fourth, and so on. 4, 3, 2, 1. And I need to find the product of each of those possible outcomes in each sequence of the event. If I find that product, that'll tell me the number of possible ordered arrangements. And keep in mind that's equivalent to 8 factorial. That's why 8 factorial will tell us the number of ordered arrangements of 8 objects. Okay, another quick example. How many ways can the letters A, B, C, D, E, and F be arranged for a 6-letter security code? So I've got the letters A, B, C, D, E, and F. So if you want to think about it using the multiplication rule for counting, so I've got a security code where I have to rearrange A, B, C, D, and F. So there are 1, 2, 3, 4, 5, 6. There are 6 letters. I have to arrange them. I need to figure out how many possibilities are there at each step in the sequence, multiply them together to tell me the total number of possible outcomes. So any of the 6 letters could start. Then I have 5 letters left for the second spot, and 4, then 3, and 2, until there's only 1 option left for the last spot. If I multiply those all together, that'll tell me the total number of possible security codes. And that's equivalent to 6 factorial. And remember, you can type that on your calculator like this. 6, math, over to probability, number 4 is the factorial button. 6 factorial is equivalent to 720. So there's 720 different 6-letter security codes if we just have to rearrange these 6 letters. So we can't repeat any of those letters. If you could repeat those letters, if you could use any of those 6, and you could repeat them as many times as you want, we would then have 6 times 6 times 6 times 6 times 6 times 6. But because we can't repeat them, it's just going to be rearranging those 6 letters. That's why we do 6 factorial like this here. Okay, when you have permutation problems, you may have some objects that are identical within your set of objects. So you may want to order a group of n objects in which some of the objects are the same. That's where this formula is going to come from, and I'll explain to you why we have this A factorial, B factorial, C factorial on the bottom. But basically the formula for the number of permutations from a set of n objects in which A are alike, B are alike, C are alike, and so on. We could have a D factorial, an E factorial, or we could just have an A factorial on the bottom. This is the formula, and I'll explain to you why we're going to have that A factorial, B factorial, C factorial on the bottom. So let's look at a problem here. Determine the number of arrangements possible using the letters of the word mathematics. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 letters in the word mathematics. So you might say, okay, figure out the number of arrangements. Number of arrangements of n objects. Well, you remember that all you have to do is 11 factorial. That was true when all the objects were different from each other. Okay? If we wanted to figure out the order of 11 objects, well, there are 11 options for the first spot, 10 for the second, 9 for the third, and so on, all the way down to 1. So you do 10 times 9 times 8, or sorry, 11 times 10 times 9 times 8, all the way down to 1, which is equal to 11 factorial. But in this case, some of the objects are the same. I've got 2 m's, 2 a's, and 2 t's. So if you think about it, here, right here, that I've just highlighted here, that's one possible arrangement of the letters in the word mathematics. Now, look what I do here. If I take this A and switch it with this A, here's another possible ordered arrangement, but you'll notice it looks exactly the same. It looks identical. Switching those A's isn't going to change anything. And how about this? What if I switched these M's? That's not going to change anything either. because those objects are identical. So let's just focus on switching the A's for a second. So for each arrangement of the letters, so here's one possible arrangement of the letters of the word mathematics, okay? For each arrangement, I could switch the A's and nothing would change. Because there are two A's, how many different ways could I switch those A's around? How many different ways could you order two objects? Well, 2 factorial. So I've counted each arrangement 2 factorial too many times. So for each arrangement, I've counted it double the amount of times that I should, because I could switch the A's and nothing would change. So I've counted that, I've counted this arrangement right here, and I've also counted this arrangement where I switched the A's. I've counted those as different things, but in fact they're the same. That's why I have to divide by 2 factorial. Divide by how many ways could you arrange these objects that are exactly the same. And that'll tell you how many times too many have you counted each individual arrangement of the letters. But also, I've got 2 m's. How many ways could I rearrange these 2 m's with each other without changing the arrangement of all the other letters? So how many ways could I rearrange those 2 m's? How many ways can you rearrange 2 objects? Another 2 factorial. And same argument with the t's. There are 2 t's. I could switch those around. That's not going to change anything, so divide by another 2 factorial. So this will give us the proper answer to the number of distinct arrangements of the letters of the word mathematics, because switching the A's isn't going to change anything, switching the M's and switching the T's aren't going to change anything if we just switch them with each other. So let me show you how to type this on your calculator here. I want to do 11 factorial, 11 math, probability, factorial, then I want to divide that by 2 factorial times 2 factorial times 2 factorial. Now, working with small factorials like that, I know the answer is just going to be 8, but if you had bigger factorials, you might want to just type the whole thing on your calculator at once. Make sure you put the denominator in brackets so your calculator knows to divide by the product of all 3 of those things. So divided by 2 factorial times 2 factorial times 2 factorial, and then close your bracket, and then enter, and we get 4,989,600. 4,989,600. Those are the number of different ways I could arrange the letters in mathematics. Make sure when you put it on your calculator, make sure you put the denominator in brackets. If there were no brackets around that 2 factorial times 2 factorial times 2 factorial, your calculator would just do 11 factorial divided by 2 factorial, evaluate, and then multiply that quotient by 2 factorial times 2 factorial. So that would give us a wrong answer. So make sure you put the denominator in brackets there. Okay, the other type of permutation problem you may have is when we want to consider the number of order arrangements of n objects taken as an... Okay, so far what we've looked at considering the number of order arrangements of n objects taken as the entire group. But what if we don't want to arrange the entire group? What if we just want to take part of the group? So that's where this counting rule for permutations is going to come from. I'm not going to fully explain this formula yet. I want to do a problem with you using the multiplication rule for counting, and then explain to you why this formula here works. So the number of ways to arrange in order n distinct objects taking them r at a time. Here's our formula, and I'll get to that in a minute. But first, let's look at this problem. Let's compute the number of possible ordered seating arrangements for 8 people into 5 chairs. And for now, let's assume the chairs are in a straight line. We're not going to do any sitting around a circular table problems yet. We'll get to that later, but for now, the chairs are in a straight line. We've got 8 people, 5 chairs. How many different ways can we arrange 8 of those people into 5 chairs? So we have a group of 8 people. So there's our n, and we want to take them 5 at a time. There's our r. Now we could do this using our multiplication rule for counting before I even worry about this n and r business. So let's do that first. Remember, multiplication rule for counting, if one event can occur in m ways and the second event can occur in n ways, the number of ways the 2 events can occur in sequence is m times n. Okay? And if there is another event, like event r, we'd have to, how many ways could R happen, and multiply that by R, and so on. Okay, so we have 5 chairs. Chair 1, 2, 3, 4, 5, and so on. Okay, 5 chairs. Let's figure out how many different options, or how many people could sit in chair 1. So there are 8 people. How many of those people could sit in chair 1? Well, any of them could sit there. We have 8 different options for chair 1. For chair 2, well, 1 person is sat in chair 1, so there are 7 people left for chair 2, and then 6 people left for 3, and 5, and 4. Number of arrangements, 8 times 7 times 6 times 5 times 4. So on our calculator, we have 8 times 7 times 6 times 5 times 4. Hit enter. 6,720. So that's using the multiplication rule for counting. 6,720 different ways that I could choose 5 people from a group of 8 to sit in 5 chairs. And those are the number of ordered arrangements of the 8 people into 5 chairs. Now, let's try using the counting rule for permutations. So you may see the formula for permutations written like this, or you may see it written with the n in subscript, written with a big P beside it, then an R in subscript beside it. This is probably normally how you'll see it written, NPR. So let's figure out how many ordered arrangements are there for 8 people taken 5 at a time. That's what that 8p5 means. It means how many arrangements of 8 people if we take them 5 at a time. We're going to use the formula. The formula is n factorial over n minus r factorial. And don't forget from our formula, this first letter here, first number there is the n, second number after the p is the r. So let's plug it into our formula and see what we get. N factorial, that's 8 factorial, over n minus r factorial, so over 8 minus 5 factorial. So we have 8 factorial over 3 factorial. Now let's simplify that fraction there. So 8 factorial, that means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Divided by 3 factorial means 3 times 2 times 1. Now let's cancel out the factors of 3, 2, and 1, because I have 3, 2, and 1 being multiplied by each other on the top and on the bottom. So what I'm left with, once again, you'll notice this is the exact same as what we did using the multiplication rule for counting. We're left with 8 times 7 times 6 times 5 times 4. Notice exactly the same as what we had here using the multiplication rule for counting. So we know that's going to give us, once again, 6,720. So that's why this formula here works. Okay, so let's use that formula one more time. So there are 8 teams in the new Metropolitan Division in the NHL's Eastern Conference. Metropolitan Division just got introduced this year in 2014 into the NHL. These are the teams in the red box here that are in the Metropolitan Division. Now, how the NHL works is the top 3 teams from each division will make the playoffs, plus 2 wildcards. Let's not worry about the wildcards for now. The top 3 teams from each division make it into the playoffs. So let's figure out how many ways can the teams in the Metropolitan Division, keep in mind there are 8 teams here, how many ways could they finish first, second, and third? So how many ways could these 8 teams be arranged into the first, second, and third rankings? So if we think about it, here's the 8 teams. How many, there's 8 teams, any one of those 8 teams could finish first. Carolina could finish first, or Columbus, or any of these 8 teams could. So there's 8 options for the first spot. Now, Pittsburgh did finish first this year, so I'll put them in the first spot, but technically there were 8 options. Now, how many different options? If one of the 8 teams has been taken, how many options are left for the finish in second place? Well, there are 7 teams left that could finish in second. Now the Rangers finished in second this year, so I'll put them there, but there were 7 options for second place. Now, how many options were there for third place? There were 6 teams left. Any one of those 6 could have finished third. Philly finished third this year, so I'll put them there. But there were 6 options. So, to figure out the number of possible arrangements, just find the product of the number of outcomes in each sequence. in each step in the sequence. So 8 times 7 times 6 will give us the number of total arrangements of those objects. So we can just do 8 times 7 times 6, and it would give us the number of total ways 8 teams could finish in first, second, and third. So 336 different ways we could have, sorry, was it 336? 336 different ways we could have teams finish in first, second, and third in the Metropolitan Division. Now, instead of using this multiplication rule from counting what we just did, we could once again use our permutations formula. NPR equals n factorial over n minus r factorial. So keep in mind, here's our n. There are 8 teams in total. How many ways could they finish in first, second, and third? So how many ways could we take 8 people and put them into 3 spots and arrange them into 3 spots? So our r is actually 3. Let's plug these values in. So 8 factorial over 8 minus 3 factorial. That equals 8 factorial over 5 factorial. If I simplify this out, if I was to expand 8 factorial, it would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 all the way down to 1. So if I want to cut off my expansion, I can add in a factorial symbol and write it like that. Because what does this mean? This means 8 times 7 times 6 times 5 factorial, and 5 factorial would mean it would keep continuing to 4, 3, 2, and 1. And what do I have on the bottom? I have a 5 factorial on the bottom as well. So notice those will cancel. That's why I cut off the top there. So once again, I have 8 times 7 times 6, which equals 336. 336 different ways that these 8 teams could finish first, second, and third in their division. Let me show you a shortcut for typing this in on your calculator. So if you want to figure out how many permutations of 8 objects taken 3 at a time there are, all you have to do is type 8, go to math, go over to probability, hit the NPR button, which is number 2. That's the permutations button. So we want to do 8 NPR, so that means our n value is 8, and then you have to type your r value. So how many objects from the group are we taking? We're taking 3. Then hit enter, and it'll give you 336 again. So there's a shortcut on your calculator if you don't want to solve it algebraically like this. And that's it for the permutations lesson. So make sure you remember permutations are about the ordered arrangement of objects. So make sure you watch the next lesson for combinations when the order of the objects is not going to be important anymore and the formula will be altered slightly. Alright, thanks for watching.